I don't know. It's your internal.
Yes, I think the speaker is the power off.
Yeah, no, okay, so you have the remote control here. This one is but I'm not sure we are right now.
Is this here? What's that? I don't know.
Usually is the data on silicon.
Sensor data sensor technology 1.8. Yeah, okay, so it's not
Technically is a webcam. It was problem.
technical. But one is not technical, that's from the last. From
Oh, last.
maybe problem.
I'm seeing this. And there's that also. And that's what. Okay, so this is for the projector, I guess. Yes. No, we don't need to. We don't want to project from here.
I understand. I mean,
Yeah, I guess
We could do that. We could do that. Okay,
yeah,
fine.
I guess
We could do that. So yeah, I'm just.
but I forgot to ask Benoit, but somebody said Benoit met her.
Yeah.
And that's
Hello.
to come back now.
Dominique told me also that it's very job. So let's thank you for adapting the schedule. Because,
Yeah.
Initially it was planned this morning, but finally.
Yeah, no worries, no worries.
Very, very critical issue, so I couldn't make it this morning. So you should say that I'm the only one. Thank you for being adaptable.
There's something missing for it. So yeah. J'ai récupéré ça. Non, qui est le ça là. Ouais. Using the laptop, can I need to up the function for switch on? Ah, ouais, d'accord, okay, so we need to. Okay. Goes like switch stuff. Okay, yeah. Okay, the usual UK plans. So hopefully it should work now. Yeah, okay, good. Epson PG, yeah, okay, so it works. For the speaker, yeah, I think it works. The microphone, I'm not sure we are using the right one. I'm not sure we are using the right microphone.
Yes.
Eh non, I don't know. Yeah, et, ouais. Et pour ça, tu sais comment... Tu peux parler, Dominique?
Can you hear me? Oh.
Alors,
Oh, okay.
oui, 1, 2, 3, test micro, test micro. This is the micro test. Yeah, you can hear me well?
Yes. Subhat, can you
Lovely.
talk?
Hi, everyone.
Can you hear us?
Yes, loud and clear. Thank you.
Okay, sorry.
But Nouredine, we're not totally sure what we should talk about. So you're the big boss, right? And
Come on. I'm here, just let me know, just let me precisely say a couple of words. First of all, thank you for accommodating this meeting because it was a little bit confusing. Really, I wanted to make this meeting this morning, but then I had some critical issues. I asked you, and you were so kind actually to be adaptable, and this is the main issue. I mean, you are already very smart, intelligent, because you were able actually to adapt. And you know that the future is comes to the people who are able to be able to adapt again. So, and you have been able to adapt. So, thank you so much for this. The second thing is that this is actually my visit. Well, I came here on last day, but still only a couple of days, so I was not able actually to make any meeting on DCART. But my first meeting here on DCART is this meeting, and I wanted really to try to discuss on some of the barriers that we are experiencing so far regarding from PDF, just to let you know also that recently it was on, I don't know, it was on Thursday, Friday, it was on Friday, last Friday. Last Friday, I went actually to Snack Island on the demonstrator of PDF, which is Masera. So just to be there and to be really familiar with the concept. Unfortunately, I was planning actually to meet with Juan and the others this week. What they are in the way actually. Vietnam, suddenly it was well. And unfortunately, we were planning actually to meet, but it was not possible to meet. But we have planned actually to meet together so that we can solve as much as possible the problems that we anticipating data. Well, this meeting actually, we wanted to share what's the status of this situation of this demonstrator. Before coming here, I had actually lunch with Romain, although Romain is not involved with EDF Lab, he's now national, but still he expressed actually a lot of interest and making the link actually with Lab. And the main purpose here is to discuss on the status now of this demonstration, because we'd like, and this is really what we agreed just a couple of hours ago, we agreed that we would like to put forward actually the energy demonstrator to become a key use case that can be actually discussed with the local agencies. But before that, if possible, that just we try to solve whatever is the barrier that we're experiencing so far, typically on the data and what EDF can do and how can we speed up somehow the process of putting together on the demonstration. Is that okay, Blaise?
That's fine, fine.
So that's what we are. And having in mind that one thing interesting is that starting from September, Benoit should go here for 1 year, and then this is also something that can pretty much give a boost because he will be here starting from September. Myself, I'll be back here most probably, and this is what's planned so far. I'm planning to be back here on February. And I'm planning to be here also with Enedis. With Enedis, and we are planning also to make the connection with SP. It's already done, actually. We have already done meeting with SP. And hopefully that we can also put forward so that we with the interest of making something even better than what we planned so far in Mazela or in Primo.
Okay, good. So what do you need from us? Do you want some recap of what we've been doing? Maybe
what's going on right now, and how can we proceed given the situation today, given the where we are and how we proceed for the next steps.
So maybe you can choose the demonstrator from EDF. That would be the most reasonable one. You have that, right? Not the model 01, but you had like 10, 20 slides, I think.
Yeah, but
I don't remember who did that. So you know the plan with the different kind of models. I don't remember. Was it you who were the meeting in August, I think? And Remy, you were there. So Paco was there, I was there. Arvin, you were there also. Don't remember who else. Benoit, Remy, you were there. Arnaud was there. Peng Feng, I remember. I don't know who else, but so anyway. So where?
I think I can find out the slides we had at the meeting, maybe.
So yeah, to tell you, so Senaco Island, so Mazera and Primo, it was the original plan. And Primo, I still don't know. I'm not today, so we don't have the data from Primo, right? That's one issue.
The agreement is, I remember that. The agreement is there. After anyway, data from data, Primo data are synthetic data. And correct me if I'm wrong.
It's just
Primo data are synthetic data, right? It's not.
For this, I'm not sure. I think this is handled by Lalita. I'm not sure it's a real data or it's synthetic data.
Yeah, just one thing is going to which one did not tell me, I'm watching actually, saying that there is an agreement, exactly an authorization to share data from Primo, at least whatever is non-confidential, of course. So there is this agreement, and what's interesting is there is an agreement on the format of the data that should be shared. And what he said is that the file should be actually uploaded on Teams, and the file is up to and still until today the file is empty. And he is actually asking me if it's possible to remind you to upload those data on Teams with the format that was agreed. Specific format on different kind of data, for example, the SIT GFE building drawing, the GDC GFE building drawing, the SIT building profile, and whatever it is non-confidential. There is this agreement to post and to put those data on Teams. So he's just trying to tell me, please remind them to remind EDF actually to upload this data on Teams as it was agreed.
Yeah, because if you have the agreement now with SP, with TUM, and so on, to share that, we should have access. I mean, like, it's just a matter of you going to the EDF Teams and you just put the data in the CARE Teams, right? The create Teams. Because it's what we have done, right? So for Mazera, it was done very efficiently in March. Romain did it actually. Were still in charge, and there were much less party involved. Also, it was purely EDF, so it was very easy for them. They had it, and they just give it to us, and it was very efficient, and we are very happy because the data is very, very good. So we see that it was
the one from this one is wonderful.
Super nice.
The 1 second resolution data for load,
for 1 full year.
Load and generation, 1 second resolution. And almost clean.
For Primo data, even for me, I don't have it.
No, but Primo, it's I mean, I had the talk with Sebastian and Tobias. So you have two stuff in the Primo data. You have the grid topology, that one is made up, so it's synthetic. And you have the building demand, maybe both cooling and electrical. And as far as you remember, it's not your data, right? But I mean, it's okay for the use case, but we just have to all to be on the same page. That the Primo use case or the Primo demonstrator will be an online simulation. Just that we're all aware of that. I mean, for me, I'm okay.
Okay. So yeah. So Norris, I think for this product, I will try to ask Edward to get data from him, and I can upload to the SharePoint of
you don't have access to this.
I don't have data.
Okay. So you should ask somebody an EDF who is working on Primo product, because there must be
Lalita. I think it was Lalita. No?
It's always Lalita, but Lalita is no longer working.
Yeah, she left. But who?
Because your name is also no longer.
No, Robert, that's why I just had a leisure. He's no longer with EDF Lab, but he's EDF International.
I see.
He's still in Singapore. He's working on EDF International, and well, it's EDF, so EDF Lab, it's EDF. So he's willing actually to do whatever needed to encourage and to facilitate.
Okay.
That's the message I got from him.
No, but the Primo data, I guess, because they were synthesized in Atium. Because it comes from Mesmo, so you have it's open data, by the way, Mesmo. So it's a building model, thermal HVAC system modeling, etc. That's the same model we use in the IntraCreate program that we have. And for the electrical load profile, I don't know who was in charge. It was at the TUM level, I guess. But who's the point?
So somebody at EDF should have this data, right? So if you know who, you can tell Pengfeng, and Pengfeng can just go and see the system and send from him. And the contract is signed. If I So there's, normally should just take a matter of
Authorization, so that's, shouldn't be a problem.
Yeah, exactly. Yeah. So now everybody agreed, and so because again, so we have done a lot of things on this particular Mazera thing because of the data. And if we don't have the data, we can't, even if it's synthetic. But if we have the data for this particular thing, even if it's synthetic, at least we can work on something which EDF would work with the same data, and it's good.
But I think the discussion was to actually have the simulator, and so that we can build our own data sets.
So that's.
Was it about Primo?
So on Mazera, there was that, but then it's what they provide. So again, it was a EDF purely thing. So EDF, they gave us their prototype.
The earlier discussion, there was agreement, Bogdan, he was somewhat right. The earlier agreement is that we get the real data from Mazera, from Primo simulated data.
Yes.
So that's the.
Yeah. But on top of that, what we need with Bogdan is that we don't just need the data. So the data is something important, but we also need, the model.
Right.
Let's say, and the simulator
Environment.
and then if you want to. The thing which tell you, if I put that, then here is how the thing is there.
Right. So the simulator is already public. So I think there is a GitHub repo.
It's a more linear model now.
So that.
So that we should have, and for Mazera they give us also.
So there are a few papers published, and the model is public in the GitHub repository, if I'm not mistaken. And I assume that's where the data is coming from.
But still Benoit is asking me to remind that he needs those data.
The data they use, and we can use their GitHub repository with this data, and it would be easy. And EDF have it, and everybody agreed. So now.
One comment, just to be sure that also we're all on the same page. So for Mazera, you have there is the microgrid layout, but the data.
It's not actually enough for Mazera.
In Indonesia, because in Mazera there is. I mean, you went to visit. There is no living load. I mean, I don't know the status right now, but.
No.
And they succeeded. They made also actually, it was 2 years ago already. They succeeded to make it work.
Yeah. So you can have 4 hours of working environment, etc.
Yes, and that's what's interesting actually, because they succeeded to make it work.
In practice, implement a controller and see how it reacts to this simulated load, etc.
Controller, they operate in the controller, and they get data. And that's what's interesting actually, because we are interested in the controller basically.
Sure, exactly. So
I think the control that was tested was the EDF store and forecast control, or the control that you implemented in Mazera for those tests that Nouredine is mentioning.
The control really implemented in Mazera is for now is even for now is role based.
There's no prediction. It's not the cloud service from store and forecast.
That's true. It was a big for enjoyment. We talked to Romain. It's true that he said that they can test, right? They can test other controller, and that's the whole point.
The software system at that time is not ready, and the software engineer in our lab is trying to fix everything so that prediction algorithm, optimization algorithm may be implemented in that system maybe in the future. So, but this is still in progress, not finished yet.
Okay.
But this is an opportunity because you're right. It's an opportunity. The first controller, because it was very important to demonstrate it works first, and it was very basic controller. So it was very basic controller. But the idea behind it is that it's possible around to test other type of controller, and that's why also Roman was interesting actually, and that's also opened up actually the door for us, because we can be able to probably, I hope so at least, that we can if we design something and then we try to compare with the basic ones, then we can see with the reference, then we demonstrate with respect to the reference to the reference. Here's from my certificate to say hello. I'm just here to say hello.
The original class.
Ça va. Et toi?
Optimisation.
C'est bien.
Store and forecast.
Ouais.
Does it ring a bell, this name?
I don't know that part.
Tu m'envoies son, à qui ou c'est je passe par toi?
I was not involved platform.
D'envoyer rapidement, parce que sinon on va pas, ça va être comme d'habitude.
I think that
Non, mais vas-y.
that provides that kind of service, cloud-based MPC control. And I remember in one of the meetings we had with Roma, you mentioned the store and forecast.
Mention.
Yeah, but it was at the very beginning of the project. So that's why I asked you, forecast optimization came from EDF store and forecast or from EDF lab here?
I don't know.
Ok, ça marche.
Okay, so yeah, so the thing is, we started with these two things, like Primo and Mazera, and with Primo wasn't really going much further because of the data we were expecting. But then you were working with Sharat.
Yeah, not on Primo.
Sharat, if I'm
Not exactly on Primo, but something which looks like Primo. I mean.
Very basic.
Yeah, in fact,
CityLearn, it's called CityLearn.
CityLearn, yeah, okay.
The very difference between Primo and Mazera or CityLearn is that CityLearn and Mazera, it's the energy system. So basically microgrid and you just exchange flow of energy. Primo, you have different nodes and you have a grid analysis. Yeah, that's the only difference.
No, but the thing is that what's interesting also with Primo is that it's on kind of city grid.
Yeah.
And that's interesting because we have the building, etc., which we don't have actually at Mazera.
Exactly.
Yes, so that's Primo. It might be interesting. The only thing is that again, since we had that agreement, we have the authorization for non-continuously data, and it's just a matter of uploading those data of the teams. So he's in charge actually of uploading those data teams.
It should be Pengfeng, but Pengfeng needs to get the data from somebody, and so you.
So it will be somebody at TUM, I guess.
At EDF, at EDF, in contact with you. I mean, with in EDF in contact with you that you.
I can ask Tobias. I mean, I was with him earlier.
Yes, who in the EDF is their contact point, and so.
Yeah, current contact point for Primo and then
for any EDF, and pass it to Pengfeng, and Pengfeng.
Yeah, it's better to get the data from EDF.
Yeah, exactly.
Yeah, not
not
from
TUM.
First of all, you just said that he will actually discuss with Edouard, right? Talk with Edouard.
Edouard told me if you want access Primo data, I need his validation approval. So before I get access to the data and share data to DCAS, I need his approval.
Sure. Do you want us to talk to Edouard? I mean, maybe it's easier if I can do that or putting the link in CC and just ask Edouard. We have this agreement. Can you allow Pengfeng to have access to that transfer? And then,
We can definitely facilitate actually this agreement, this contact with Edouard. The thing that was a little tricky is that this change in the contact person, etc., within EDF. So things were smooth, and then of course when people they come, they have to get familiar with what's going on before, of course, taking decisions. Right? I fully understand the process. That's why, if needed, both, of course, Blaise, myself, or anybody else, we can also get in touch with Edouard so that we can explain the process in a way, and then maybe it eases to get this validation. Understand? It's fortunate because we planned actually to meet with Edouard.
He's leaving that.
Some coincidence, but we planned actually. Again, anyway, so we can both Blaise or myself, we can revert it to.
Sure. Go on. I mean, I think you are more indicated than me to mail Edouard about it, and I can do it. That's okay. So anyway, so that was the starting point. But then in August, things changed a bit. Then EDF they come up with, oh no, so let's forget Mazera and Primo, more or less. And they propose some mix of both, I would say. I mean, that's how I see it, at least. And they propose us a new Model 0, Model 1, Model 2, where Model 0 was basic, very close to Mazera, but with a big important point, which is now there is some, you can buy from grid. So you have interaction between your microgrid and some grid, where you can buy exact power to it.
And frequency.
And some
And
frequency.
services? Oh,
No.
The idea is to use, it's like investigate the VPP,
Yeah.
provide ancillary service.
So provide what? Primary,
Everything.
secondary, tertiary? Yeah, but which one? Which one? Primary, secondary, tertiary? Spinning and spinning?
Contingency secondary, I think.
So to turn the contingency market in Singapore.
We assume we can do this.
Of course, it doesn't exist yet, but
So not the balancing, not the frequency, contingency markets in Singapore.
no frequency.
No, I don't think there's,
Contingency, that's why.
yeah,
Because you have energy contingency and balancing market in Singapore.
there's
Frequency is not contingency.
there's no ancillary service in market in Singapore for now. So I read from the Singapore electricity regulation rules. They basically have two kinds of frequency regulatory service, primary service, and contingency service. There's no balancing concept.
No, and demand response they have as well. Is this something that you investigate? They have a demand response market, meaning that you can reduce your demand according to the needs of the grid. So it's a market that they have in Singapore as well. Primary frequencies for the big power plants. So the market you are targeting is contingency market, not demand response. So it basically is the possibility to provide upward.
Upward or downward.
Downward as well.
Yeah. Because we have battery inside, so we can do downward frequency regulation.
Okay, just to understand.
Okay.
Understand. Model 0, is that basic that is close to Mazera?
Yeah.
The purpose is to use the kind of model of Mazera as a BBP to provide some services for the grid.
Yeah, it's I think it's possible to use microgrid support power system frequency
And add an additional stream of.
That's a service. That's a service.
So it's, in fact, it's not a different model. It's just you have the same system. It's just different use cases. My voice is terrible.
Yeah.
It's the same model, same system, but just a different use case in which you want to add another stream of revenue.
Me to share, please.
Allow me. How can I share it?
Some slides.
We have slides on model 0. The 1 and 2 would be.
Yeah, sure, exactly. But I mean, if Feng Feng has something, I'm happy, but that's at least a lot better than. Okay.
Yeah, that's what we
After the review.
demoed in the summer school. I mean, whatever the presentation. So it was based on that model.
Then while the Feng Feng is looking at this model, so you have the model 0 and then model 1, model 2.
Yes, so I'm not. So they were adding things more and more, more and more complicated with a multi-grid. So more like Primo, basically. So yeah.
To my understanding, no, it's still at the microgrid scale, but either you do autonomous, typical Nouredine mode, either you interact with the grid buying, selling price, and I guess you interact. The ultimate stuff is you buying, selling price plus ancillary services.
No,
but that's all model 0.
Huh?
That's model 0.
we already do that.
That's already model 0.
And with the ancillary services?
Yeah.
So just some reservation in the battery or.
Do you get paid if you deliver upward regulation or downward regulation?
Yeah, you do. It's here.
Okay. Bon.
Okay, then the other model, what's the other one? This is based on microgrid. This is microgrid.
So yeah, you are the microgrid. And then, so it's here on the screen. So you are the microgrid here, and you need to decide what to do with your load, your generation, and so on. And you can sell and buy to the grid. You can provide ancillary reserve power for the utility in order to do frequency regulation. And you are also in charge of your own frequency regulation in your grid. So we also look at the microgrid level to be sure that you don't you stay around 50 Hertz inside your own.
Well, when it's interconnected, there is only one frequency, both for microgrid and the grid.
Yes, so I mean, the grid you are not responsible, but it's just if the grid asks you to provide the service.
Standalone, it should be like.
Yeah.
Where does it come from, the signal, what you reserved power for utility?
So
what's
in the optimization, basically there is a benefit. There is for reserving some battery power for doing this regulation.
So you have what? You have an input parameter.
Model.
You have a time series input parameter that model the activation profile
Of the regulation?
Yeah.
No. The model is not at that level.
I mean, we don't. I mean, we assume it's zero all the time, but we still will reserve the power for that.
So there is a benefit. So there is some cost benefit, and you try to maximize that benefit. So basically, you use your battery reserve.
So you don't answer to activation signals extra. It's just that you will have 10% of my battery, I will get that more money.
Yeah,
It's a constraint.
It's essentially a reservation.
Yeah. So what we do now is we said, okay, yeah, we reserve some power for batteries that we cannot touch, we cannot use.
Yeah.
So it costs us money. So the grid give us money for that.
Right.
So the first we use at some point.
So the assumption is the grid will use that.
Okay, it should at least compensate my loss of revenue.
So there is no real time.
Just let you know how it works actually in practice. Practice, in order to participate in frequency regulation, we have two steps. First step is to do capacity reservation. That's the capacity reservation, which means that you reserve the capacity that can be used later on, but you reserve only the capacity that in terms of megawatt or kilowatt, whatever it is. That's the capacity. That's the market, but this is ahead of time. This can be day ahead, for example.
Yeah, that's exactly what we do.
And then, depending on the actual operation, depending, of course, on the need for that frequency regulation, then you may, of course, call for that reserve.
Sure, yeah.
And this is energy signal. That's megawatt hour. That's how it works on double scaling. Because that's
So the thing is, because
in this model, what we are doing is more about the reserve.
The reserve that was zero data about what you have said, the energy things that they ask, we put zero all the time. So it's like it's never using it, but then I cannot use it because I reserve it in case.
That's the capacity.
But in fact, to translate it, it's not the objective function is not to maximize the cost with the revenue with the grid service. It's just to operate the system, but they have a constraint on the battery reservation.
It's also, I said, still in construct. Okay, so day ahead, we say, okay, fine. At noon, we can reserve this much power to do this service if necessary. And we wanted this power, okay? It will be reserved for the grid operation. So then in operation, because we have zero data about it, just assume that it never asks anything. But if it asks, we are able to, it's easy to change if we have the data.
Okay. So it's a capacity, as you mentioned, it's a capacity reservation.
It's a capacity reservation.
And you get,
It's a capacity reservation, but then once you have, of course, understand that because this is a process for capacity reservation, which is in fact, for example, in France, this is done on the balancing mechanism, and it's in the bidding process. That's in the bidding process. And then that's up to the operator later on, and up to the operator, once he calls actually the capacity that is selected, because we have different capacities and then arbitrage, depending on different parameters. And then once he calls actually the capacity, then the owner of the battery or the owner of that reserve, he will be rewarded for
additional reward
on the energy market.
Additional reward.
Additional reward.
Based on actual.
Necessarily additional reward. Because the first process is on the bidding for capacity. Once he gets into that, he gets already the reward by the fact that he was selected for the capacity market. And then once he is selected, if he is called, then he gets additional reward.
Okay.
Except if it's charged, but that's not for battery. But
that's for battery, but
not
this
for
mechanism is available. This mechanism is available for
yeah,
the
but most
generator.
likely it will be the same.
It's available for the generator. It's available for the response. That's what we have aggregators actually. It's the negative generation. And we have some generators to do that. And it's available also. That's available for battery. So you have the three.
So okay.
That's how it works.
And so that's model zero.
So model zero has two pieces. One is the look ahead contract, which is
commitment,
buy sell. So you commit to a certain buy sell profile, and this reserve for frequency response. And then there is the real time aspect where we use those constraints to actually
you try to mitigate uncertainties, and that's what
exactly developed. So that's what it is.
Yeah. So that's model zero.
Okay.
And on top of that, so we also have the PACO side, which look at your operation, how does it affect the frequency? And
so this is the peak, the delta F. So when you switch the set points of any component, to change the kind of millisecond change in the frequency, the delta F. So he computes that. So there is some differential equation model for computing this delta.
So basically, the head optimization problem is to calculate the setting point.
Yeah.
Then you have the setting point based on the reinforcement learning. They use reinforcement learning as a real-time controller. So the time resolution for the AI-based reinforcement learning method is millisecond or is in second time resolution. But for the optimization.
Yeah.
For the optimization,
is doing okay. So we know because we have done it. It's not that at all. So yeah.
So yeah, but this was the next part, which was basically Paco was trying to model this.
The grid, in fact.
So the delta F. So
the grid inertia.
Right. Exactly.
Ceasing. Okay.
That peak.
Okay. So based on the equation.
So here like it's the power plant inertia and so on. So he modeled the power plant inertia.
Correct.
From where?
Oh, he's modeling the internal flux, etc.
He's not. We have taken the question from EDF.
So I guess that here you have the generator inertia, etc. That stuff.
So what he did was he took the differential equations.
So this model, I put this model here. You have a lot of differential equations. Okay. This differential equation is written by me.
The model and they give to Paco. Okay.
This differential.
This doesn't work. This model doesn't work for the frequency.
Yes, right. So this is just for.
You emulate the grid. Yeah. Okay.
Listen to me. So this differential equation is for a islanding microgrid. We want to verify the algorithm from Paco to solve differential equation in a very fast speed. So this is just for the verification. And if you want to operate an islanding microgrid, that means your inertia is very low. So it's really possible to for your frequency go very high and go very low. But this is if you are an operator of islanding microgrid, this is not what you want in actual operation. That's why I said I list all of these differential equations. But this equation is just for the operation of islanding microgrid. It's not really related to the previous one.
Yeah, it's completely different use case. Okay. Because for me, I understood at the beginning that you model the grid inertia so that you see the impact of your grid.
So what I understand, from another paper again, is that just assume that your grid connection is cut.
Yeah.
So now the grid connection is cut, and so now you are islanded.
Yes.
And that's where this thing would make sense.
Yeah, there's two separated problems.
Yeah.
It's you cannot combine.
And that's why you would be responsible yourself on the frequency of your microgrid because now there's no grid and you are alone, right?
Yeah, but
That's what I understand.
For the frequency of regulation, again, on the other model, actually, because, for the frequency regulation, we use, even for low frequency, for low inertia, for the situation, for low inertia. We have different dynamics that we call electromagnetic equations. So the electromagnetic equations are, of course, the fast reaction in terms of milliseconds.
Exactly, yeah.
In terms of milliseconds, where actually, if you have mechanical masses, then they don't
Takes much longer, yeah.
dynamics. So in terms of what we call stability, including stability at low inertia, we don't use the fast electromagnetic equation, but because it's not compatible with the time responsive controls.
Yeah, correct.
Okay. So that's why I was a little bit when you
Yeah, so
A stupid question. In the standalone mode, who will control the voltage and frequency, the genset, or you can do that with the battery as well?
Battery in Madeira Island, Madeira microgrid is battery dominated the system.
So the battery build up the grid.
Battery established the system voltage and the frequency.
The reference.
Stupid question. It means that the battery supplies the losses in the system.
Losses on the system.
Yeah, because if the battery is the one who regulates the voltage.
And
all the losses are supplied by the battery, all the losses in the system.
Yes. In Madeira, this is the case.
Yeah.
And your generator, your diesel generator is in grid following mode.
Okay.
So
and you charge up the battery, because if it supplies the losses, then you will.
Yes, right.
Yes, that's what I've seen. That's what I've seen exactly, because you have the photovoltaic, you have the Genco. Okay, a genset. You have the genset. You have the genset, and you have the battery. And actually, the genset is on grid following. Yes, that's grid following, and they try to have the reference at the battery level. Even when this photovoltaic, they have the variability, and then it's the battery that takes the reference. That's what.
That's why I established the power electronics equations over there to see this system inertia is dominated by battery, and its interface to power converters.
Okay. And so that using Paco algorithm, because you can solve in real time those differential equations. That's the whole idea, right?
Yeah, so so he solves the numerical equation by going to Fourier transforms. And then he still do something else to even go put that into some neural network in order for even faster things if you want just the delta F.
You simulate in what the environment is your.
No, they are the equations. Because we can do that. We can do that with another software that is.
We
can do that right away. Yeah.
Okay.
So basically, what Paco did is simulated the equations, got data, fed it into, trained the neural network with that data. So the neural network is like a surrogate model.
Little bit, Hassan was the.
We have a PhD, for example, a PhD today who's working on kind of similar with the battery system, because this PhD is working actually on EA controllers. Okay, on EA controls for the microgrid.
Okay.
Specifically microgrid with low inertia, which is exactly which we're here, and we have a specific environment of development, and then we already have a very, very nice result that we can actually, because it's so we can transpose it here eventually.
My idea is that if we just focus on islanding microgrid when we are doing the economic dispatch or operation for islanding microgrid, we may want to ensure the frequency or the voltage in your local area does not violate the prescribed range.
Right.
The frequency will not go to your frequency will not go down 51 hertz or fall down 49 hertz. So I think if we can integrate this kind of surrogate model, this surrogate model actually represents the inertial dynamics of your system. So if we can substitute this kind of surrogate model into optimization, then we can ensure the frequency safety or voltage safety even in your planning or dispatch phase. So
Dispatch phase. So you want to do, the idea is to do a dispatch but for standalone system.
a standalone system.
I mean, the cheapest stuff, you don't need a dispatch, is that you use the solar as much as possible to charge a battery and supply the load.
But what if your system is a bit, it is very large? What if your system is very large, just like NTU campus or the building?
But the thing is that economic dispatch makes sense from the mathematical point of view if you have different source of generation that display price cost discrepancies. If you have only a PV panel and battery, in terms of operating costs, to minimize, you have nothing unless you account for the battery aging due to cycling.
Yeah, what he means actually.
So dispatch is okay. You a genset that costs
just
8 per kilowatt hour and a grid that costs
what he means actually is a traditional economic dispatch. Traditional economic dispatch is based on marginal cost. Yes. Here you don't have a marginal cost of the generation. If you don't have a marginal cost of the generation, what you have actually just which can be another type of economic dispatch, is actually to optimize the based, for example, on the forecast of the PV, and then you make a dispatch when you have to charge the battery and when you have to supply the load, depending on your forecast and how you optimize your system, which basically turns to kind of same equations. But the model is different because you don't have cost-based data. I mean, cost-based economic dispatch.
Economic dispatch, different emission, and you want to minimize the overall cost of the overall emission. If you're in a standalone system, the only stuff that costs you operation is the fuel of the genset, for instance. So basically, if you just want to minimize the use of the genset, you maximize the use of your solar. And if you have too much solar, you charge everything in the battery, and the genset will take the remaining energy. Maybe after, I don't know, in the use case, you can also do an arbitrage on the battery, number of cycles, etc. And then indeed, you may need optimization.
Correct me if I'm wrong, Benjamin, but if I remember your plan for model 1 initially, the next model that you want to look at was to integrate this frequency constraint in the optimization.
Yeah, that's my suggestion. That's my initial suggestion. We can.
But then in the last meeting we discussed that the time scales are very different.
So what's the? Now I understand that. Well,
So
we understand that model 0. What's model 1?
So you have the slide for model 1?
Yeah, we don't have. Okay, we don't have the slides, so it's good.
I'm pretty sure
We don't have the slides I don't even remember who gives the.
Was to combine the two of them.
Yeah. So this, let's say, whatever this. Equation.
Yes.
No, but so anyway, as I say, it doesn't make sense. This equation has no sense, but it should be something else for.
It's okay. Yeah, for me, the time scale is different because this model it works for millisecond scale.
And what we are doing right now is we are targeting 5 minutes, let's say,
or even hours.
Right now we are doing even less, but we need 5 minutes. Or I don't know. Does it make sense? So that's.
I think this just
The idea would be to include this time frequency, this frequency model right from the look ahead stage when you optimize for the next day your schedule. That's it?
No, it would
Not necessarily look at the real time. But the real time operation is also.
like you are cut to the grid.
Yeah.
Then you need to react, and then you need to provide your own.
We provide set points, right?
Because otherwise we will have the whole meeting on issues.
Yeah.
I think that my suggestion is that if you have slides. Yes, model 1.
We need to see that. So we don't even remember what it was. It was 3 months ago, and we don't have the slide. I checked. I don't think I have the slides.
No, but it's interesting perspective. That's really interesting.
We just need to understand the objective and constraints of the operational phase. What is it?
I think, your slides were very clear, Peng. So if you could show that how the different models
Yeah,
you
let me find out the model.
And what I remember that there were many microgrids and they would adding maybe vehicle charging, vehicle to grid and so on. Yeah, like they were putting a lot more things, not just a microgrid with one thing, but then a lot of things.
But the thing is that this is on a simulation perspective because you have Mazera Island is on the other side.
No, but yeah.
It's just an idea.
Actually, so.
No, of course. Mazera Island was just, forget about Mazera Island.
Okay, so model 1 is here.
So here is just an idea how we can touch hybrid AI concept.
So model 1, that's what, okay, so you train a neural network from the output of an optimization.
Can you go back to model 0 just so that
Model 0 is just neglect the rectangular.
So model 0 is what we discussed so far, which is there is this look ahead contract that you need to sign.
Okay.
And then you do a real-time control of the assets, in this case, battery and the diesel generator, based on these constraints that you have from look ahead. And the only thing you do is you buy cell from the grid and you reserve some battery power for the frequency response. Okay, and you get some benefit from that.
Okay.
Model 1 is that plus
the frequency.
This omega constraint at the bottom, the system frequency constraint at the bottom, where this omega is coming from these equations, the differential equations.
But approximate with a neural network.
Approximate. Well, okay, that's
what
what Paco suggested, but doesn't have to be. I mean, that's
okay.
So somehow you get that omega constraint, right?
But we are here already, no? I mean, so compared to where we are today, what's the difference with model 1?
PCS.
We don't do that omega, right? The last
But it's what
okay. So as I just said,
incorporated in the optimal.
As I just said, this is just a reference. This is just an idea or suggestion how we can play around hybrid AI. Of course, this frequency
is not up to EDF to tell us what we need to do with AI. We are. I mean, tell us what you need. And we are here to give you the solution. I think we discuss that every meeting. We discuss that. You know.
So the idea is to integrate the approximate model as a constraint in the dispatch.
Correct.
As Arvin mentioned, I think I have the same concern as Arvin, is that the summation in the objective function t from 1 to 24 suggests that you have 1 hour time step, and the delta t in the green rectangle, is it 1 hour or no?
It's millisecond, right?
It's yes.
The output. Okay, the output of this neural network is a scalar. The scalar is what is scalar is the maximum frequency deviation.
Oh, okay.
So we want to limit the frequency deviation with
It's a delta.
Deviation is for varying load and generation. So P, and P. LT at every 5 milliseconds or 1
Yeah, something like that. Probably.
Etc. This is 1 hour resolution. Depending on the dynamic of those guys, indeed, you will have every millisecond varying frequency, approximate thanks to your model. But from the look ahead perspective, you are not going. I mean, I understand that you have signals at 1 hour resolution here, not 1 millisecond for the next day.
We
are not going to
discuss this before.
Yeah, we are not going to predict solar generation for the next day at 1 millisecond resolution.
Correct.
So that's why we're talking about these dynamics are not compatible with frequency.
Exactly. Yeah, exactly.
No, they're not compatible with look ahead.
There's one thing on reality, but from Peng suggests that he put those equations in order to see what the neural network can be done.
Yeah, you're right. That's right. This is my idea. Yeah.
The reality, just how to interact with the neural network.
This is a way
to visibility, just visibility. But later on, when this is demonstrated, we need to put the real equations, the real situation, which is today, for example, is the resolution of half an hour. Rather than half an hour for scaling, but for the regulation, it's seconds and minutes. Yeah, but this is just to, I understand this is just to show the feasibility, how to get yourself.
So, again,
maybe just to clarify what Remy's confusion is.
There is a summation.
So there are two different optimizations we solve for.
Show me 2 blocks.
Right. So one is you do a look ahead, what we call the contract.
That's
right?
this one, because you have a summation over time.
Correct.
Okay.
Right? So you have 24, the next day's forecast, 1 hour at 1 hour granularity, whatever, and you commit to buying or selling something from the grid and reserve some battery capacity for frequency response.
This is the way it works in reality.
Right. So this is one problem we solve. Now, given these constraints, so now I go to the next day, right? I have these constraints imposed on me from the previous contract.
Commitment.
I do a real-time control on the operation.
And here you can account for the frequency.
Currently, I think we are doing, it's 30 minutes or
1 hour.
It's still 1 hour.
But yeah, I'm trying to do it at
Yeah, but we have data at a granularity of
seconds, so we
Okay.
And the plan was to do it at the level of 5 minutes or something like that.
I have something.
Okay.
And the suggestion, what I understood earlier for model 1 was you take this real-time problem and you incorporate that omega constraint.
So it's not the problem, it's the subjective then.
Right. This, the one coming from this equation.
But of course, in terms
Is that
the equation, it's not from
no, but
the equation.
there are two things. Okay, so of course it's absolutely stupid to think you will put millisecond thing in the hour time.
Yes.
It's absolutely nonsense. Okay.
Okay.
But now you can still want to take into this account this thing and see what constraint do they have globally on the 1 hour sunset.
Okay.
That's what I understand from
So
that.
it's actually not the
Okay.
way to solve it, but it's still an interesting question and you want to integrate basically all these things.
I understand that. I understand.
What kind of constraints they can give? Okay, so
So it's like some ramp rate or some set point limits that you have to put on
something like
real
that.
time
Or something else, I mean, yeah.
given this omega.
I think this neural network, this substitution can be anything
Yes.
we are interested
That's what I
in.
understand.
The frequency here is just an example.
Because here, just to make it also all more widely, here you can see what neural network can do. And my understanding here is to set, for example, the frequency limitation neural network. Okay, that's what I understand. That the neural network can be also used actually, for example, to speed up the control. That's possible because you're able to make classification very easy, for example, and then you discriminate between different cases, and then it can be rule based or whatever. That can one possibility of using the neural network in the control, not necessarily on setting the frequency, because usually the frequency is a constraint that is set. That's the constraint. It is set. For example, in Europe, I mean, if it's an interconnected grid, it's clearly you have two levels. One level is plus or minus 0.0. And the second level, which is called the emergency level, which is plus or minus 0.5 hertz. That's, you cannot touch it. I mean, we don't need neural network to tell us what's the frequency or what the frequency limits, because that's contractual. I mean, there is no issue to do that. That's the way it is. But once you have that, once you have those limits, whether it's a normal variation, whether it's an emergency limitation, sometimes you have different kind of controllers. Well, in France, for example, the control where you have this primary and secondary. Basically, the primary is just a proportional controller, and the secondary is that you add the integral term to the controller. That's basically what's primary and secondary control. Well, that it works. Where we are now a little bit tricky, where this classical model is on the limit, because we have low inertia. Low inertia makes somehow say quick reaction. We need additional models, additional control to tackle those low inertia things. So that's why we can have this neural network embedded so that we can see neural network, whatever it is, AI upgrade, for at least for the control, and maybe making what we call currently virtual inertia. Okay, what we call virtual inertia. That's what can be done, and that's what we expect. And then Hassan is doing this kind of things. But my understanding is that how to couple the two things, the physical model and then the neural network for some example. That's my understanding. It's feasibility. I think it's more feasible.
Solvability of this problem? Yeah,
Yeah, it's a matter of usability because we don't fix the limit of the frequency. We don't fix that. It is what it is.
and just also, if so, I understand that the neural network can be should be included as constraints in the problem, but depending on the activation function, sigmoid or tangent hyperbolic, it's nonlinear.
Yeah,
So then you will have to solve a nonlinear problem for real-time control, and then you come back to your previous problem where you had the nonlinear equation. Because if the activation function of the ReLU, okay, you can do piecewise. Okay.
But maybe can I ask a more basic aspect, just for my own purpose?
Anyways, let's not discuss about it.
Yeah, okay, yeah, because I want to ask a more fundamental question. Suppose I'm doing real-time control at the granularity of 30 minutes, or let's say 15 minutes. Okay?
5 minutes. Yeah.
5 minutes, let's say 5 minutes. Does it matter this millisecond? Can I really do anything at the level of 15 minutes to really regulate?
Milliseconds, honestly, day,
Primary control.
milliseconds,
Yes.
it doesn't make sense.
Right.
And it's even introduces even instabilities.
Right.
It introduces even instabilities if you make it on milliseconds.
Below 1 minute, below
So the ideal actually is that to fit within 30 seconds for primary control. This is just to give the boost for reacting in front of any disturbance, imbalance, whatever. That's 30 seconds, 10 seconds. That's good. And then in order to recover actually the frequency, this is just to give the boost the first boost. And then you have to recover. And in terms of automatic control, you need to minimize the static error. And to minimize the static error, you integral level. And then this is secondary. And secondary means what? Means that you have kind of optimization in a subtle way when you have different kind of generation. And you reset set points so that you coordinate the different output of the different generators participating in frequency regulation.
Okay.
After in our field, research-wise, mixing those two time granularities is super interesting. If you want to do more grid planning or sizing some battery stuff that can do dispatch and on shorter stability on the shorter term. And research-wise, how you accumulate those two time resolution to the optimal sizing. But for the control, there is no.
Did you think? Okay, so because I was doing the real-time control in microgrid system.
Yeah.
So I know in some operating point, some power flow operating point, the system may not be stable.
Yeah.
I mean, it's more signal sense. So.
No, that's he's talking about the small signal stability.
Stability. Yeah. So normally when we are doing economic dispatch, the result is only the static solution, and maybe you really apply this static operation, your system may not tolerate this operating point because the damping of the system is not enough, or does not meet your requirement. So do you think it's also possible to use a neural network here? Assume that the substitution of this neural network in the optimization problem is solvable. Assume that.
This is backtrack. This is easy answer. There is an easy answer. When you have sufficient damping. When you have sufficient damping, they see in the equations of small signal stability, then actually you may not need neural networks because you have sufficient damping. But the fact that you have low inertia, then you have less damping. And when you have less damping, you need faster response in control. And to have faster response in control, that's why we need neural networks or the EA techniques. That's what we need. Because we have lowered the damping coefficient with the low inertia. The damping coefficient, it comes actually from the winding of the machines. Okay, that's where it comes. The winding of the machines, and because you have the inertia of the machines, and all this, that's what provides actually the damping coefficient. But if you don't have that, imagine that you don't have the genset. Imagine you have only the battery and the PD.
Yeah. Even in this kind of okay. So in large scale power system, when you are talking about stability, you're talking about two synchronous generators swing with each other.
No, that's different. That's different. No, this is low frequency oscillations. This is low frequency oscillations where you have interzone or local interzone. That's different. That's totally different. What I'm talking about is really when you run your small signal stability analysis. You run your small signal and then you draw your modes. Modes of operations, and in the modes you get actually the damping coefficient along with participation factors and so on. You know that. With that damping coefficient, of course, it has something to do with the oscillations, but actually it has something to do with the movement of the poles towards the real axis. Okay, so that is totally linked actually to the ability of this synchronous machine to act as a damper. But once you don't have those synchronous machines as a damper, then you have faster reaction. I mean, you can have, for example, nadir, which is the frequency, drop whenever you have whenever you have a disturbance. Then when you have this damping coefficient lower, then you have a larger nadir, which actually may not recover the frequency.
Right.
Okay, so there where we need actually better control, because if we don't have that, we have our control that works perfectly. But with this deep nadir, then we need the different kind of other controllers, and we need the help of the EI in that case. That's my perception. That's what we're working for. You don't get it.
The paper you passed us, it was exactly that. They were talking about nadir. You had the nadir, the thing had low inertia. So I can already relate to the paper you sent us like 1 month ago on the Icelandic microgrid and so on. I mean, so I'm not okay. I'm not and I'm not an electrical engineering at all. Okay, so it's zero. So, but from understanding, at least I read the paper and I listened to you. I can relate both. Okay, it seems very related. So
yeah, I can send.
But you should read the paper you sent us.
So I at TDF, what you would like be to replace the primary control with such a controller at the end. That's what you would like to do at TDF, to replace the primary control with this control. Yeah,
primary control of
what do you mean
by primary? The fast one, local one.
Yes, a millisecond one. Or?
Yes.
Yeah, millisecond.
That's the question. That's the question.
Millisecond. We don't have direct control.
Yeah. There's nothing about primary.
Okay.
So okay, so it's a good question. So I don't know. So the control, you control at the level of 30 seconds? 30 seconds.
It's within.
Okay.
Within, it's a matter of between 10 and 30 seconds.
Okay, something like that. Okay. And so, but you think, okay, but of course it would be nice to have some inputs, right? Some guy telling you, okay, you should go toward this or that. And this should be at the level of 5 minutes, 1 hour.
So then we have two levels. The first level is within 30 seconds. And the second level is within 10 minutes.
Okay, fine.
That's okay.
Okay.
Within 10 minutes, and within 10 minutes, we should recover the frequency.
Okay, so yes, this is okay. No, but so
whenever there is a disruption.
So what we have been looking at here was
Just to clear what Nouredine is saying is only about the frequency regulation.
Only about the frequency.
So what about the rest then?
Well, the rest with the voltage.
I think Blaise is asking about component control, like set points for.
It's actually, you have two levels of the set controllers. You have the first set level of the controllers. It depends if you're dealing with voltage. The frequency, you have the first set that everybody has to, there is normally, there is a sensor at the output of the generator. There is a sensor that measures the frequency.
That's right.
And there is a set point which is 50 hertz. That's the set point. Local, that's local, okay? Nothing related to outside, this is local. And then you have the controller, which is on real time in matters of seconds, that reacts to the difference in the difference between the measured frequency and the set point.
And that's rule-based, but can you just tell you if you
This is-
do that? Yes.
Well, it's not very rule-based. It's really, there is a statism, call it, there is a statism. There is a kind of a percentage of the power that you have. It's proportional regulator control. And it's totally decentralized. Every machine, every single.
Fine, I understand. Fine.
The problem is that whenever there is a disturbance, if all the injection point, they do the same thing, sometimes they inject more than.
Yeah, it will create an imbalance.
And a central point needs actually to run on optimization in real time. That's why 10 minutes. You need to run this. And then they find out what would be the good setting point.
For everybody, one, yeah.
From the fact that you are close or whatever.
Yeah.
And then there is a sending. So everybody will get the setting.
Yeah, sure.
And then the machine will now not regulate to the basic one, but it will to the new setting. That
Oh, yeah, sure. And it will
and then we'll see that there is a good regulation.
Yeah.
So that's how it works.
Yeah. Okay, good. So
And then what about the load, basically controller for the load, like demand response?
Okay, demand response actually extreme normally so far. Demand response have two parts. Okay, there is one part that is it kept today on the balancing mechanism. Okay, which means after 10 minutes.
Right.
Okay, it comes only after 10 minutes.
Okay.
Which for the time being, it is used mostly for generation consumption balance, but afterwards. Okay, not for the real time. There is also the frequency regulation. I mean, the demand response that is only in emergency mode. Because if we want to use the demand response for frequency regulation, we need 2 points. The first point is that we need the confidence, which means that if you activate it, I mean, you know that it's going to work, which is not always the case for the demand. Different from the generation. The second thing, it needs also to be compatible with the statism, like for the generation. It cannot be just from 0 to 1. It has to be compatible with the statism as well. And that's you have to implement it, which means that you have to implement some kind of what we call droop control. Okay, droop control on the load, which is not that easy that if you put it on the generator. That's how it is with but it's coming up. It's coming up.
Even discrete, you have discrete frequency response. That's sure.
Yeah. Otherwise, you will have a discrete thing to say. Okay.
Okay. And then when you do the real-time control of just balancing the supply and load, I mean, just set points for the battery, whatever, discharge charge. So that happens at the frequency of what, 30 minutes or?
In fact, it's the real time is the primary control of your converter of your battery. So you have a loop control that will compute the reference in power, but after you have the internal loop of your power converter, the current loop, for instance, that will. Yes, that's what I was mentioning.
Basically, your battery which will provide what you want.
Excuse me?
I understand you have something very local and which work at the level of second or
even less, yeah.
But then the order you give it will be at the level of 10 minutes, right? 10 minutes, yeah.
Bunch of minutes, yes.
Less than 10 minutes. Yeah, less than 10 minutes.
You have the serving control, so it's the planning, half an hour, what you look ahead, then you would have the real-time control. The secondary in which you send the ultimate set point.
Yeah, and then the operational.
Usually the primary, it's on the manufacturer premise. I mean, it's.
Yeah, sure, I understand. So it's a genset and it's totally distributed and you just do.
Totally decentralized.
Okay, fine. So can I show you? So it's some very new thing because it's from this weekend. Okay, so it's well. So we have something which work. So everything we have done before was with the idea of 1 hour. Okay, basically in the dream project, everything was at 1 hour set point. And then what they try to do on the dream project, they say, okay, but 1 hour it's not realistic.
Yes,
we want to have more often, operational stuff. Okay, so they try to brute force it, And they came to us telling us, okay, we tried. So we can write the thing, we can press the button, but then it takes too long. Okay.
It's long to train.
To train, yes, exactly.
Yes, they run an RL.
It takes 1 month to train or something.
well, okay.
After you train one time, you say, oh, it doesn't work well, so I need to change parameter.
That's the pain.
It's impossible to rush.
And this is even for a small system.
Yes.
Even for Maserati, it was really effective for Maserati.
The problem is, at least what we saw so far,
Multiplied
there's
by
not enough
12.
data.
Everything is multiplied by 12.
Yeah, I understand that.
But if at the level of second, yeah, it's steady. Yeah. So anyway, so it's something we have worked on, and so now we are being able to go from the 1 hour to 5 minute operation.
Excellent.
So, and from what you tell us, it's the right level to look at.
Okay.
So of course, it multiplies the number of control points by 12. Okay, so you need to take 12 times more things, much more frequent. You have much more variables. If you talk about MLP or things like that, you have much more variables. So even more constraints. You have much more uncertainty because now it's not every hour you have some weather cast, but every 5 minutes now you have some weather cast. So you multiply also the uncertainties.
Right.
So of course, if you want to brute force it, which ADF, so let's try that. The runtime would be awful. You would be at least 100 times slower. And that's assuming linear scaling, and nothing is scaled linearly. Okay, it's much more than that. Okay, so it's awful. So now it's what we have done using really hybrid AI, and this one is really pure hybrid AI where we use different things. So MILP. So we use 2 different time scales. So MILP at the 5 minute and RL at the 1 hour. Okay, so basically RL is just here to give some incentive, some indication to MILP. And it also allows MILP to only have a look ahead of 1 hour. It doesn't need to know what happens else because it just relies on the RL. So like that, what you do is you have much nice things. So like training time, it only takes 1.5 times more, which is like 1 day and a half instead of a day. It's easy. And we don't do it twice. So I think we can even bring back to 1 day probably. 1 time versus MILP, because we have much less variable now because we don't have a look ahead of 1 hour, but just of 1 day, but of 1 hour. It's actually 10 times faster per time step. And because we have basically times time more time steps, it's basically as fast as the other one.
So in real time, every hour, I don't remember, every hour you have forecast now for the next hour, what happened?
So now what we have exactly, so instead of having a forecast for the next day, 24 values, only need the forecast for the next hour.
Okay, at 5 minute resolution.
At 5 minutes resolution.
Okay, and that you...
That basically is just, it's going down or it's going up, depending on the time. Okay, like the day is going up, so something very simple, okay? And it's much more reliable. At 1 hour, it was very hard to have a good forecast. At 1 day, sorry, it was very hard to have a good forecast. At 1 hour, it's very easy, okay? All our forecasts are very close to the reality. And we have developed a reality forecast.
But let just me just interrupt you for 5 minutes because I'm interested actually on what you have done, and this is really good, actually, very interesting. The question is this, because another issue that is very important where we need really some help on the artificial intelligence tools and is that we need to face actually the uncertainty coming from the forecast.
Yeah, exactly. Yeah.
And the problem of the forecasts, particularly if we need to forecast, for example, PV. PV, when it is at the local scale, and even here in Singapore, it's even more challenging. When it's local scale, we have large errors.
And
exactly. Today, nobody actually is really able, in general scale, I mean, to have better than 30% error. Well, I haven't seen an area actually that one was able to have reach 15%, which is tremendous, actually. Tremendous best. But this is on one case that is treated specifically. I know that it can be generalized actually in, on different other cases. So this is very challenging.
Yeah, perfectly. So actually, as was the data from the Indonesian island, so I can show you. So here, this is the two consecutive days, actually.
But you never get this kind of curve.
No, so this is the reality. This is the data. So it's just to show you. No, it's show you the forecast.
I can show you the data. This is look like it.
No, it's okay. So it's not the forecast, it's the data. Our forecast doesn't do well.
If it's in 1 hour, you may. If it's just an interpolation, because usually what they had but they measure.
Yeah.
It has the.
This is measure on the PV panel, you know? Yeah.
They have this, but most of the time like this.
Exactly, it is. I mean, so, yes.
Okay, so,
I just give you, I mean, as you can see, there's only 1 point every hour, right?
yeah, that's why.
Yeah.
You put the point every hour and then you put the temperature.
Exactly, yes.
That's
We fully agree.
for the controller. That doesn't help. See, for the controller, we need those.
No, sure. Yeah, but yes and no. I mean, yes and no, because when you set a set point at 5 minute time granularity, it doesn't. I mean, so sure, you need to take it into account in some sense, but you won't tell it. Oh, change every second, change like that.
Second.
You just change the thing at 5 minutes, depending on the average. Basically, yeah.
So that's why.
Yeah, sure. I agree. So what I mean is, okay, so this is, so yeah, I fully agree. So if you want to forecast at the 5 minute granularity over 1 day,
No.
impossible. It's absolutely possible. You will be off.
For the time being.
Yeah.
Time being.
Fully agree.
Something is a kind of hybrid forecast, so first hour at 5 minutes and then 2 hours.
It's exactly what I was also bad. Anyway, so fully agreed. But so now if you do that at 1 hour, the next hour, then we can be much better.
Right.
Okay, so and I mean, again, from the data we have, it seems to be much easier. Okay, so of course, what happened in 5 minute granularity in 3 hours, it's impossible. Okay, but basically, what will happen in the next hour? Sure, we can be wrong, but we are not too wrong too much because the weather doesn't evolve that fast. So that's why we think this one a big point, and that's why I show it. Yeah.
The cost, what is it? Only the fuel cost or something else?
No, everything. Fuel, buy from the grid, the ancillary system,
The reserve.
and using the battery. And so there is fuel, but yeah. Not. Okay, so yeah, I won't go on so that we have. So yeah, as I said, so yeah, I fully agree. I think this is a big selling point that now we only need a forecast of 1 hour, and this should be much easier to get than the forecast of the next day. Okay, and again, from the data we can follow it much better. So we haven't done a full research on that, but basically we have some, you know, before we look at 10 data points for the day and we were very wrong. And now we look at 10 data points for like 10 different days and we can predict it.
And don't forget, there is penalty if you are far away from the profile you committed in the head, etc.
No, we commit.
Now it's
We could have penalty. And so even with that, we still have very good operational cost. So it's not as good as the one with 1 hour, but now there's much more uncertainty and so on. So
that's
I mean, it can be
operation cost.
So we with the parameter we have,
fuel cost, grid cost, and genset cost, grid cost.
Yeah.
Cost. It isn't related genset cost here.
The fuel. Fuel cost.
The fuel cost a lot.
And grid cost.
The grid cost for sure, and a bit the price of using the battery.
And grid cost is time of use, I think, day, night.
No, it's not day and night. Every hour has different price.
For the grid?
Yeah, for the grid. And it's Singapore price. Okay, so we need the 1 hour thing, but yeah.
That's hourly spot market.
No, we use them in Singapore. Yeah, you took the Singapore price. We
use the Singapore price.
But I heard that it is a half an hour, not hour.
Half an hour.
Yeah.
It's half an hour.
What, 1 hour? Right. So yeah, so we were quite happy with that. So and we are only the very first result we have. You know, we didn't even improve anything. So yeah, I think this one should be nice.
Excellent.
And yes, last but not least, it's set by design. So basically so the second level is MIP, so it's purely deterministic. And you can add into it, and that's what we have done, constraints saying, even if your forecast is wrong, you should still be sure that you are able to, last minute put the genset and be able to fill your load.
So the AI comes from the way you predict the look ahead, then the profile you're going.
There is RL. Okay, so there is RL there's both RL and, okay, so I can show you.
In the first phase.
There's both RL, no, not on the first phase, on the second, so it was Swiss time scale, right? It was the hour time scale, the day rate thing, this is purely MILP.
Yeah.
Then we have the hour EL, that's RL. And then we have the 5 minutes, and 5 minutes is MILP again. So RL is just here basically to give MILP.
The forecast.
You should try, no, not the forecast.
The predicted
Try to
target.
target
Yeah.
this state of charge in 1 hour. And try to do it, and if MILP cannot, he won't do it.
Yeah.
He just will do the best he can.
You know, we should, once this is present result, we should make kind of case comparison with Hassan.
No, Hassan is
Probably doing something else.
some cases.
No, it's not the same use case, I know, but
Exactly. No, we may want to compare with what Jonathan is going to develop.
Jonathan probably, but Jonathan on storage. That's
Huh?
storage, Jonathan on storage, no?
Yeah, there will be storage. It's behind the meta application.
Okay.
So
The same.
something we thought, so it's what we discussed with Subat, we haven't done it, but exactly that. So trying to see what MILP can do if you have 5 minute things for the next hour and then 1 per hour after that.
Oh,
Okay. So which would make sense. It's reasonable in terms of number of constraints. But then how much we gain or lose compared to that, that would be interesting. Because now what we do is we only forecast MILP, even if we give it MILP, even if we tell it exactly what will be the real data point at each hour,
yes.
we beat it a lot.
The best optimal. So
Yes, the best optimal from MILP.
Yeah.
What is the primary output of the MILP?
It's a set point at each hour. Yes.
Set point for the.
The SOC in 1 hour, right? That's how you
The set point means the control action.
the set point.
Battery charge, discharge, and genset.
We keep the same MILP at the 5 minute level, but we try to replace the RL, which was telling you the state of charge you should target in 1 hour. We just replace this one by an MILP. And the MILP basically would try to, it was our original one, which every hour tell you which state of charge you should, which set point you should have, but then which state of charge you should target. And even giving it
For what they
full knowledge on everything which should happen. Yes, perfect data. And we beat it. Because it's only at the 1 hour time point, so it doesn't know the 5 minutes. So that's why we said maybe by doing 5 minutes first and then an hour, this would give it more knowledge and probably here would do better, but still, with full data and full knowledge, and which it doesn't have it. So yeah, we are quite. So yeah, I have the data.
So based on our experiments with this data, this test is, I think for what we found is the MILP does very well in terms of optimizing if your forecasts are good.
Yeah, exactly. Yeah.
But of course, the forecasts are never good. So, and the RL does well in managing the uncertainty in the forecast compared to what MILP does. So essentially, even though the RL may not give you in terms of the optimal results as good as what a good MILP could do with good forecast, but RL does well with dealing with uncertainty. So I think with this hybrid approach, the idea is that the RL kind of deals with the uncertainty in the forecast in the 24-hour.
After I would play the bad cop role if I would have to review the paper. You compare with MILP with deterministic forecast. Other would say, why not doing stochastic optimization, robust or distributed robust optimization, or De Carlo, whatever, or stochastic MPC.
Or take the most sophisticated forecasting model.
So that's the first point. And second point is MILP does best if you have perfect forecast, because in fact, the model embedded in your constraints and objective is the same model that you actually consider.
Yeah, exactly.
Which is not the case in reality.
Yeah, exactly.
And in fact, that's for me.
What do you mean? So so maybe let's discuss that. Okay, so it's this one. So for the 1 hour time scale, we have RL. Okay, here. Okay. Then for the stage 3 at 5 minute operation, we compare two things. One is real data, perfect data. So you assume you know exactly what will happen. And the other one is a real forecast, local forecast, okay? So this one is really what you can have today with here we don't see that all. Okay, here it's not the perfect data. Here it's
the forecast 1 hour.
Yes, we do, yeah.
Right.
From what you said, you think we are using here, perfect, okay? We can compare with that, but we are not using that for sure. We are not using the future data.
No, for me, the perfect would be deterministic. You have the offline simulation, you take historical data, and you do MILP about it. And that you have the perfect that you cannot reach in real life.
It's a reference.
The lowest bound.
Yeah, exactly. That's the reference. But we are very close to the reference. So that's what I mean. So anyway, there's not.
For me, I mean, it doesn't matter that comparing it to it. What's really interesting for me is that given the fact that I have uncertainties and error in forecasting, and what they heard that you are telling me that the URL is able to actually to handle those uncertainties better than for SOC at least. For SOC, I don't know how it is possible, but this is itself is a very good result. Actually.
Yeah, sure.
This is itself it's already a very good result. And then if based on uncertainty, it was possible actually to provide, for example, the right control for the SOC, for example, that's already a very good result.
So maybe you should clarify, explain the P2 model a bit. I mean, just to, so the RL, at least from our experiments, does better than using this P2 with MILP.
Yeah.
And P2 is the forecast for.
So basically, exponential averaging of past hourly data.
So basically, just look at what happened at 8 a.m. for all the previous year. And of course, you put more weight to what happened very recently to the previous days than what happened 1 year ago. Okay. So there's a big decay on what happens a long time ago. So basically, it is just that. Okay. And this works. And at the hour time scale, it doesn't work very well. I mean, like if you look for 24 hours, it doesn't work very well, of course.
That's your forecast.
On the data we have, because the weather evolves very fast, and from one day to the next one, it's very different here. But at the 5-minute time scale, I mean, at the 1 hour horizon, to get something which is very
the P2.
And we correct it with, the level where we are compared to where we are supposed to be. So that's how that's P2 actually. P1 is just, we use this local average. And P2 is we look at the very, at the last 15 minutes, basically, and you see how much it varies compared to what you were planning, and you apply this coefficient to whatever you plan in the next hour. Yeah, it's nothing very.
Just assume that this difference is always the same, is always linear, because it changes.
Sorry?
This difference, you said, from where you are and where you should go. You said that you compute this difference and then you apply it.
It's a multiplicative factor, but if I'm twice as much as, if now I'm twice as much as I was supposed to be from yesterday data, then the fact I would do this, I would multiply by 2 whatever I expect in the next 5 minutes. And then we are not far away from it.
Yeah, but this multiplicating factor is not always the same, it's changed.
But we look at what happened. Like if I'm at 2, the multiplicative factor is just based on the 3 last data. Let's say now I'm twice as much as what I was supposed to be. 5 minutes ago, I'm 1.5 times much as what I was supposed to be, and then 10 minutes ago I was 1.8. You just average that, and this is the coefficient.
It's like the Euclidean
yes.
Reconnaissance de forme.
Yeah, it's something very, very simple, but it doesn't work well at 1 hour time scale. But it works very well at 5 minutes till 1 hour, because it's close enough that what you do is okay. So it's nothing very incredible. And you're right that here we could use AI also to learn some coefficient of what to do. I mean, we could write. Probably we could optimize that.
But it's interesting.
So, Blaise, one question I had is in that table you showed, the last table, the latest result.
Okay, so yeah.
That's perfect, yeah, this one.
Yeah.
So what does it mean, MILP perfect? You assume only the stage 3 forecast is perfect.
Data is perfect. Yeah.
No. I mean, 1 hour
Only the 1 hour.
You know, but at 1 hour, and this is at 1 hour time scale, and this is at 5 minute time scale, stage 3.
Contract generation is fixed for everything.
Okay.
And we're comparing list.
Okay, so if I get the perfect is MILP perfect at 24 hours and MILP perfect at 5 minutes. That would be the perfect.
But
the base, the lowest bound.
So why is the first one? Yeah, the first one.
Because it only look every hour. It doesn't know that you look at every 5 minutes.
Which one?
This one. Okay, so again, RL, what it does, it gives you, and both are doing that. So stage two, what it gives you is the SOC you are expected to be at in 1 hour.
Correct.
Okay, both, everything. Okay, so MLP to do that is just optimize every hour and say, oh, this is better for me for our previous thing, which was hour based. But it's not what will happen, because what will happen is every 5 minutes you will have some changes. It doesn't know this, okay? And RL knows this because it's trained with this kind of information. So that's why RL can outperform this MLP perfect. Because he understands better the low level things, which other ones totally don't know. So of course we could get something better by saying, okay, fine. Assume you have 24 times 5 minute resolution and you feed that to MLP, but then there will be like 1,000 of variables. That would be more challenging.
Stage 1 is not perfect here, if I understand correctly.
Stage 2, you mean?
No, stage 1.
Stage
Yeah, no, stage 1,
I know, but
yeah.
It's not perfect.
Okay.
But it will be possible to have the
Stage 1 perfect, stage 2 perfect, because this will give you the minimum cost.
Right.
No, but again, stage 1 don't. It's okay because they are all using the same stage 1. Okay, so it's fair. They're all using the same contract. Okay.
Yes, but having the 3-stage perfect gives a reference compared to which everyone after you compute the precision compared to this best reference.
Sure, I mean we could do that also. I agree with you, but so again, something we can do even fixing stage 1 is stage 2 and 3. You could do this. So you could do the next 1 hour every 5 minutes. You know exactly, and then 1 per hour, and then you optimize that. You give the SOC. And then that's what you would use. So I think here we would get something better than we should get something better than RS. It's supposed to be better, okay? But we haven't done that. We just talk about the better. So yeah, but we will before you leave, we will have not very hard.
So now the idea is to as I asked Kevin, okay, from that where do we move? So that's the
model. Now the next question is.
So this,
okay.
I think that now this is done again from my understanding. This description is that that's done, of course, for an hour for this SOC. Now it moved to 5 minutes, but it's not always on 5 minutes. It's really good on 5 minutes. That's really ordinary.
Yeah, sure. So, yeah.
Now I think that the next step is really to put those inputs or those algorithms within kind of stability model. Stability model that works with differential equations. Or we can use, for example, any model. I don't know which model you use at EDF for assessing, for example, stability and frequency. Do you use, for example, that we do use power factory, for example?
We use power factory.
Power factory is Eurostar? Or power factory?
Power factory.
Power factory, yeah. The next step, I think, is that we try to do that and put them in the power factory as input. Then you can follow actually the time dependency of the parameters. For example, it's the frequency from seconds to minutes, 5 minutes, etc. So that's then we're going to the next step.
Yeah.
So that would be something probably nice to do.
Yeah, we can go in this direction.
Yeah, well, how you make those simulation live? Because to make those simulation live, you need super resolution, load profile, and generation profile too.
Well, if we take for example power factory, you can supply the loads.
At which resolution?
That's the resolution of the load. Principal resolution of the load. It should be something like normally it's the normal is there is a coincidence with the pricing, which is half an hour. It should be half an hour for the load. And for the forecast of the load, what we use, for example, we have what we call 96 points. When we make the forecast is 96.10 minutes, which is every 10 minutes.
Okay.
That's the load check. Yeah, it's quasi steady state.
Okay.
It's quasi steady state. It doesn't need to have the changing for the stability. It doesn't have to change it. It doesn't have to change it. Because that's in principle, that's when we have the big change, we have really the big change is when you have a disturbance. Okay, then we assess actually the evolution of the frequency. So we have first the set point through the static power flow equations. We have that static point, and then the load the load can be managed every 10 minutes, for example. Okay, you can have the profile of demand, but you can put the load if you have your forecast, for example, the load profile. What's the sampling of the load profile?
Here was 5 minutes.
You can use the sampling of the load profile of 5 minutes if you have it, because we don't have it all the time. That's the question, because we don't have the load profile every 5 minutes. We have the load profile every 10 minutes on the forecast. But if you have the forecast of 5 minutes, then you can enter it. You can enter it in the moment. That's not the issue. And then you can, the same thing, if you have the 5 minute forecast of the PV, I don't know if it's because I don't know how it is, but or you can make a 5 minute forecast with the PV. So you can then enter it. And the process then is to see if it works by this 5 minutes that you have a disturbance, because what's important is that when you have a disturbance, you see the reaction actually. If we can keep the frequency, if the controller is able actually to keep the frequency in when it is faced to a disturbance, given actually this quasi-static data profile. That's how it works.
So you simulate this microgrid Mazera in Power Factory there?
Mazera microgrid in Power Factory. Yeah.
Okay. So then you have set points and you do what you say, okay, if my storage trips, what happened if my genset trips?
Yeah. And then
what?
Then you see if you are able to keep the frequency and the voltage, obviously.
It depends on how strong are your uncertainties, are your disturbance.
The two things. The first thing is that when you make this simulation, well, you don't know if your data are very small. Your reaction, your controller, etc., reacts to your data. Okay, but you have to compare that with the measurement to see if your model is correct or not, if your reaction is correct or not. You have to compare that to the measurements. So that's how we assess the and I guess that's what you got.
I don't know if they have done much.
For me, it's not my area of expertise.
Very super. So I guess something like that is done at the, I don't know, European level. So how do they do that? Because they don't put every factory of every.
Of course, yes, they do. That's mandatory. It's mandatory.
We have to keep the line on. Otherwise, you will not get the line if we don't do it.
They go even -2, meaning a combination of 2 disturbances. So it multiplies all the factories.
We have to do it.
So they take into account everything.
Not at the European level, but
we have at the European level.
Yeah, but not all the lines, obviously, or the big.
No, it's
the big lines.
There is a reduced.
Yeah. Okay. So you have.
But you are still.
Bit of abstraction.
But we are still talking about combination of thousands of assets.
Definitely.
You know that we are able to do, for example, even from France, we're able, because it takes a lot of time actually to make just one disturbance and simulate disturbance for the whole machines. But even for France, for example, because once, for example, we find out that one disturbance may be a very big problem, we have to prepare ourselves actually for remedial actions. cannot let the disturbance happen.
Yeah, that's it. Yeah.
We cannot do that. So we have to provide a set. And what we do actually, we take all those contingencies n-1, particularly n-1, because that is what is monitored at the level of France, for example, and we analyze them. Systematically, and we sort to see which contingency may actually be harmful, and then we can prepare for that in case of it happening.
Yeah. So, and you prefer what to add? One day ahead, one.
We have
day
we supplement it with our head.
And the real time, yeah. When you observe this intraday market, etc. Right. So, coming back, so next step would be to have this Mazera model in Power Factory, and for every set point sent by Subrat controller to do a stability analysis.
No, it's not just the stability. This because we need also. I mean, we need two things. We need to make sure that with this set points, for example, when we the NALP, when it sends the SOEC, for example, then it manages actually the operation of charging, for example, the battery, or discharging the battery when it has to participate in the frequency regulation. This is time dependency. I mean, we have to simulate the time dependency. Okay, even though without the disturbance, you need to simulate how it works in model-like Power Factory.
Okay, so in fact, that's what I was mentioning. Then you play with the discrepancies between the granularity of models.
Correct.
Because models in Power Factory is not the same as linear equation.
Correct. Okay. But then once you have done that, then you need to make sure that the stability is kept, which means that whenever you have a disturbance, then what you have implemented is still robust to keep the frequency within the range of the constraints.
Yeah, so in fact, the most important disturbance, I guess, will be if you lose PV or GenCo, and then the battery would have to supply the reserve.
For example, you have the PV that suddenly drop in output, and then of course the battery has to take over and to see if because you have reserved the capacity, and if this is reserved capacity, which should be optimal, means that it's not all, and if you have contingency that is threatening this capacity that you have reserved, for example.
So coming back,
but in Power Factory there is some mechanism to regulate the frequency automatically.
Yeah,
so if you introduce a disturbance, then it knows.
Then you can implement controllers and so on.
You can implement the controller.
So Benfeng, coming back to the suggestion you had with this surrogate model, could be something like you run a bunch of offline simulation in Power Factory with different set points for battery, PV, and so on. Do disturbances, and from that you kind of classify. You have a model that take input some set points and output is, it could be dangerous or not for the frequency, something like that. Do you get what I mean?
I'm a little old. Can I use the restless? I'm sorry.
If I followed what you suggested earlier, this neural network model, instead of being built based on differential equation, could be built based on different Power Factory simulation. That's it.
I think the even as far as I understand for Power Factory, how do you solve the electromechanical system? It's basically the differential equation.
Yeah, of course. Yeah. So.
What do you mean?
The thing is that I'm not a user of Power Factory. I mean, for me, I never go below the minute. Okay. So if apparently the next move is to go to Power Factory, you need to get some information from Power Factory and then loop and input them in your decision-making process to some extent. So basically, I'm trying to relate the usage of Power Factory to what you proposed with those surrogate model.
I know we.
Okay, you have Subrat stuff, output some set points at 5-minute resolution. Then you send them to Power Factory, if I understand well.
Yeah.
And then what?
Then Power Factory may give you some dynamics. Some dynamics of the frequency or voltage of the.
Okay. So if it's okay, if the frequency is okay, then all good. And then if the frequency is not okay, what? You said,
So what can you, it was our question also 1 month ago. So what can you do to make it fine? So it's what is basically ramping not as fast, something like that. It's what kind of solution to avoid the problem?
So you have 5-minute time step set points. You send to Power Factory, and Power Factory sends you.
It's a problem.
Okay.
So I think the set point is maybe too different from what you had. I guess it's something else now.
So again,
Is there any feedback from Power Factory to?
Yeah. What will be the feedback, and then what will be the action?
Yeah. What was the action you?
I have no. It's an open question.
But I think from what I understand, it's just okay. Maybe you have too much change. So your plan had too much change, and that's why you have a problem. And so what you should do is let's change not as radically as you have defined. Which is, I mean, it's what I understood.
Or once you issues and assets during those 5 years, but then you come back to more a reserve constraints after. Because I think you simulate this guy in Power Factory, right?
I didn't simulate system. I normally simulate system in MATLAB Simulink. And Power Factory model is built by Larissa.
Simulink will be the same because Simulink you have transient as well. And did you observe any transient frequency band or voltage if you change the set points in Simulink or no?
Okay, yeah, I to be honest, I don't know in real time in actual power sensor operation if you have a step up of your set point. What is it happening? How the system operator will?
That should be assessed actually in the model. That should be.
It will be a step or not? It's a step.
You can make a step. Basically, as Blaise mentioned, the output of that is a ramping constraints that could be included.
Yeah, I think the constraint you have, there is what, yeah.
That's why all in traditional things, all the different, they have the ramping constraint actually.
Exactly. Yeah, exactly.
From their side, not from the power system side.
No, from the generator side.
Yeah.
The generator side is a step, small step.
You can put the step that you want. For example, you put all the steps that you have two things. The first thing is that, for example, you have a step. Let's say you have a step in the load. The load jumps.
This one I understand.
So that's very easy. Okay, you jump. You have the load, and then you have, of course, the generator in principle, they have the ramping constraint, which means that's why you have a drop in the frequency because they are not able to follow the jump as for the load, for example. That's why you have a small frequency decrease, and then as the ramping is going up, the frequency can follow and then can be somehow going to be not normal, but at least it can be restored for a certain level. You have this kind of jump. You have also, for example, loss of a generator. If you lose a generator, it's also a step because you lose it immediately. And then you have from 1 to 0. And then it's like a jump in the load.
So something else needs to be over, like the battery.
Exactly. And then you have some other injection. It can be a battery. It can be another generator that has to take over in order to compensate that loss. And then it has also the ramping constraint. We have the ramping constraint for the generator, but then the battery has a different dynamics. The battery, I guess that the battery can jump immediately.
Yeah, yes.
That the battery can jump.
As long as
There's no limitation. There's no limitation.
It's not like a genset. It's not like a genset. So then once you have those constraints, then you know exactly how the system will react to different kind of disturbances. Because even when you have, for example, in real system, not in this microgrid, if you lose the transmission line, if you lose the transmission line, then you change the power flows.
Congestion.
You change the power flow, even if you don't have a congestion. Just by changing the power flows, then in the line, then the pattern, the sharing of the power between the generator has to change. Because of the power flow change. Yeah. Then you have the ramping, same thing, the ramping. Some of them they will decrease, some of them they have to increase depending on the sensing of the DF, delta F, which is the frequency deviation. So that's how it works.
So you send the set point, you do scenario analysis offline, and then you correct your controller.
Is that or offline, you already put all the constraints you need to ensure that, yeah, it's not, oh, I will do that in the next, okay, or maybe you just say, okay, I have that, I will do, and then I have my contingency plan, and I know that all of them works.
It's based on offline scenario, I correct my controller.
No, usually, for example, we did that. We did that, for example, we did for stability analysis in the past. With, particularly with neural networks and so on, not around. We were not faced to this kind of uncertainties with the PV. In the past, where we have generators and load, we don't have any uncertainty.
But in load, you have.
What we did is that because we wanted, when we wanted to simulate all kind of disturbances dynamically and to see what will be the impact on the frequency. Okay, so what we do is that we have all the system in the simulation, and then we start to have the list of all contingencies, and we simulate one after the other. And when we simulate the one, and then we see what is the impact on the frequency. And then this analysis, this result, we put them as the training, which means that we know what will be the reaction.
In this case, there's no line cut off.
No, it is like so, which means that we train the system on the behavior of the machines and so on every contingency.
Yeah.
So that, and then we train that, we train them. It takes time. Okay, to do the classification, so that in real time, when it comes this kind of course, there is an uncertainty only on load forecast. Okay, that's where there is and then the I would say the AI will only assess the difference between what is happening and what has this model, and then it decides on the control immediately, so that doesn't have to understand what's going on, because otherwise you have to book a lot of simulation to understand.
So does it use
this is reason, yes. This is used. But as I told you, the only uncertainty that we will face is only the load. We're not.
Again, if you lose some connection or whatever,
then you have to retrain the model. And that's the problem.
Does it make sense with a small system like that? Because the contingencies is just loss connection on battery, PV, or genset, or variation PV, battery.
Our purpose obviously is to scale up. Okay.
Yes.
We don't have any power flow.
Exactly. I know. But the issue is that to see if what we can do here, for example, with the uncertainty, because I'm really interested on how to deal with the uncertainty related to the PV and so on, and how the ERL can perform in this case. And then we try to put it on a little scale up for the contingencies. And mind you, is how we can scale it for real system, which are much bigger and with bigger problem, because we cannot immediately put it on this big system. So we need to start with this little system, and then we can scale them up.
You can curtail the PV in Mazera.
Yeah, you can.
Yeah.
And you can adjust the Q as well.
You don't have to curtail. I mean, it's a drop of the generation. It's
no, but it's a degree of freedom as well. If you have too much, can you control the Q as well, or no, from the PV and battery?
In a zero system, they can control the PV output, of course. So I think PV is curtailable.
And the reactive power, you control as well, or no?
I'm not sure if they have.
I can answer, because these are the questions that I looked at when I visited Basel. Yes. Well, if I visited, it's not for nothing. I have a purpose. Yes. Actually, in the inverters that are provided by Denfos. Okay. Because Denfos is providing that, and they implemented actually the reactive power control.
So it's AC bus.
Yes.
It will be used
for the AC. Okay, of course, for the AC.
Used for each.
Yes, for instance.
Correct. It's for the super.
I don't.
Yeah. So what I have when I had this visit. So, and this is clear, there is a showcase, and in SCADA system, And I visited actually all the inverters, and I looked inside the inverters. I looked inside the inverters and, to see this where it got the setting and how the setting is done within the inverters. And this power, some of them are grid forming, the other are grid following, and I looked at all of that. And then in the SCADA, we see how the reactive power is controlled for voltage control. So there is such capability, at least for what I've seen.
Then, yeah, you may have some contingencies at some point. Imagine you have a set point in active power for the battery, but you have under voltage for some reason. Then the battery, if it regulates the voltage, you try to send a lot of Q with its inverter, and maybe added with the.
Because you know how it works in Seneca Island. How it works is that you have different microgrids. Okay, you have the microgrids from NG, you have microgrids from Mazera, you have microgrids from the others, etc. And then there is a common coupling. There is a common coupling done by NTU, actually, common coupling within NTU. And NTU actually, depending on how those microgrids allowing them to play or not. Because that's for example, EDF can allow NTU to play or not. NG can allow NTU to play or not. And then they can act actually when they are interconnected, because it's possible to get interconnected. And it's possible actually to act on reactive power regulation through the inverters.
Should be taken into account in the MILP. It's what we do with ND, for instance, stuff like that.
Yeah, I think so,
because you have the line impedance, etc. of everything, and in the Mazera use case, you know the line impedance.
I don't think we know the line impedance.
But you did purchase those lines from a manufacturer, those cables. And you have
there is basically no line, actually.
It's too short.
It's too short. There's no line.
It's
basically no line because
we estimated.
There is a cable. You know this building. You know that building where the waste they come, and there is the photovoltaic panels on the top. Yeah, you know the waste. They process the waste, and then there are those photovoltaics on the roof, and then there is an underground cable actually coming. There is an underground cable coming to those inverters and.
There is no part running on the floor. Okay.
No. I think for the application for Mazera and NG microgrid, resistance will be quite large.
Yeah.
According to my understanding, according to my experimentation, but X.
They are small.
The X will be very small, very small.
Yeah, so the impact of the reactive may not be.
So basically, the resistive network.
Yeah, very small. Nevertheless, there is a way actually to act on reactive power through the inverters.
Yeah.
And that's functionality that service is offered, at least from what I've seen with the Danfoss inverters.
See if that can be done.
I have not been inside the Mazera part. I have not seen the Mazera part.
Just coming back to the control part. So suppose you simulate in Power Factory these scenarios, and there are errors and faults and stuff. Of course, the RL and the model we have is not trained to deal with those events. So what is the next step then? You give data from those events?
Because it's a lot of scenario.
If you want to train,
If you want to train
a robustness check for
if you want to train RL, you have to do the real-time interaction between RL and there's no data.
In mind, it's more supervised learning. What you're mentioning that we have
interaction real time.
Yeah, for RL, but if you want to run a bunch of offline simulation to the classification afterwards.
Yeah, because for example, you have a drop in your TV. I would imagine that the controller.
But my concern is that in what kind of situation I can write down the equation, which means there is no, which means everything can be done in the equation.
Yeah.
However, if you have a saturation function in your control system, there's no way to write it down in differential equations. So for PV, you have MPP mode. So there's no reason to write down differential equation as saturation function.
But to do that, you can replace your differential equation by a
About real time, yeah, I know.
as a that has saturation and so on. But
Just simulate offline on many things and just they use some more lamps on things.
I would say we can train our offline instead of.
Big thing. Think about the problem, not the solution. We are here for that, okay? It's not. I mean, the solution is not let's brute force everything, and let's just train RL with some super difficult things.
because
It's what we want to avoid.
So the objective of the Power Factory simulation is to
run scenario.
Yeah, and then generate some data.
Yeah, I guess exactly. You can generate data to understand what's happening.
No, if you simulate a scenario, it gives you data.
Yeah, correct.
Yeah.
And then you can start training.
Yeah. From the scenario, after you try to classify.
And then the question is a robustness question. So you have these different scenarios.
What is that directly, but then it's probably extremely stupid. So better that offline. Try to get something.
Classify and maybe in real time you can.
No, in real time I wouldn't do that. I mean, it's okay, unless to maybe check.
In real time, maybe you can take the measurement and use this classifier that you train offline to see if it's.
What I would do again is train offline.
Yeah.
Get some rules. Just use the rule online. Again, because I don't think it's constraint basically. Constraint you are learning.
In fact, okay. Now I understand the. Okay. Why you were mentioning RL, because you wanted to couple RL with Power Factory as the environment. That's it.
You can do that, but then it's really good.
It's too long because every time you have to call the Power Factory, I forget about it.
That's why you
generate offline data set.
Maybe you can.
I think generate offline data set is more doable, right?
Yeah.
So that's why.
Yeah, but I think you can use Power Factory offline to play scenario, and then Power Factory will tell you, no, frequency is bad, or frequency is good. But then how you will generate the right policy and the right decision to make.
Yeah. So I think again, offline, you do it offline to get something robust.
That's it.
More or less.
That's how it
is. And then online you can still check with this particular scenario you are playing. What will happen?
This is exactly how it happens.
And if there is a problem, then maybe you have some other things which is bad, but you only, you have some contingency plan which costs you some money, but it's okay because it's only for this.
For scenario generation, what is the input and what is the output?
Then for me, that's a big part of the deal. I mean, because in real time you will have static set point from Schubrat stage 3.
Yeah. Okay.
So I guess that when you may want to generate different scenario that's starting from we play with the variation of the set point.
For generator for
PV load, PV load.
Yeah. All the combinations.
What I'm afraid of is that in fact at the end of the day the most the disturbance with the most impact will always be the loss of the biggest generator or battery or load.
No, I need different things. Again, this is, I would say, the first approach. And to try to see how can take advantage of what has been done here with the training and then to apply it for this regulation. Then we will scale up for different scenarios. Now, I think one important that's what I heard from you, and that you have already used Power Factory to simulate Mazera, right? That's what you told me. So you did it for something, which means that you have already supplied the model with data in terms of EV generation, the battery, and the load. And then you have already simulated let's say something
first now.
You did that, right? So this is already a good thing. I mean, that's that already you have that.
Yeah, after then you have the core brick to generate a bunch of scenarios.
And then you can generate different scenarios, and the scenarios keep it easy at the beginning. And I would say, even though because you have to train on 24 hours, etc., so you have still you have actually it has in principle it has to be traded not only 24 hours, but man, that on 8,760 hours.
Because it's 5 minute long scenario, correct? No?
Okay. And if it's 5 minutes, then you can imagine how it's big for a small system already. So then it's quite challenging. And once it is training on specific, and then you multiply by a number of scenarios. That's why keep it easy in terms of scenario. One of the scenario is, I mean, you can, for example, one scenario is the just a jump in load, for example. That's jump in load. One of the scenario is probably a loss of PV generation. Okay, that's quite equivalent, for example. One of the losses, I don't know if it's possible or not, that you can simulate it because it's you don't have this duplication. If you lose the battery.
Okay.
If you lose the battery, I don't know if this is feasible because you don't have duplication of batteries that can take over, and they don't know if it's genset to them. If the genset, they are able to take over.
I guess you don't lose the full battery. Maybe you lose a bit. I mean, because I guess the battery is not one big thing. It's mainly small batteries.
And that happened.
Yeah.
That happened. Then I mean, this is a real case.
Yeah, but if it happens and you have no more energy, and then people would understand, like, okay.
In system that we have, for example, in continental Europe.
We're not there. Yeah, no, not
that's.
But you have not one battery. You have maybe you won't have one fire everywhere, and that's when you can, and you are bombed by.
Maybe with Remy on the others, we have been asked actually to do the design in the transition of Tahiti power system.
Okay.
Tahiti power system, the transition from the current carbonized mix of energy to decarbonized mix of energy. It means that it will be a scale up like this. Okay. That's what, in my mind, a scale up actually. And there we will have some batteries, and we need to check that if we have a battery with that.
No, but you may have several.
It's an island.
Yeah, so it's on the Tahiti island, not okay. So
no, we will make it on Tahiti island and in the other Swan Islands as well.
Yeah, sure. No, but you could have a different. I mean, like, you don't need to have one power generator somewhere and one battery somewhere. You can have several ones.
Then the output of the scenario is frequency and voltage.
Frequency and voltage. That's the thing. Well, because you don't have, in principle, you should have the internal angle of the generator.
I got you.
Okay, so in principle, you have to see that. Well, you can also follow it because you have the genset. Since you have the genset, you need also to have the internal angle. These are the and in that measure, it's maybe not necessary because you don't have that many line, but in principle, you should also to have, if there is any congestion generated by this issue. For example, if you have thermal current limits on the line that is exceeded. But keep it easy. Again, keep it easy. Don't put everything at the same time. So put simple things. For example, just two scenarios.
I guess what we have done here is to use a neural network to remember the physical behavior of the entire system. Am I right?
Physical reaction.
Yeah, physical reaction of the entire system instead of only battery or only PV.
Yeah, this is more reasonable to me.
Yeah, and I think that this is one of the.
And even for large-scale power system, and this neural network will also remember the power flow effects of
same methodology will apply.
Of course, yeah.
Same methodology. That's why it's interesting to design the methodology here and think about scale up later on.
Yeah, understand. Yeah.
So now, two issues. The first issue, are we clear in terms of data?
Data I will.
So we're clear, and you will respond to Benoit on his issue. That's what.
And I can ask Tobias, what's the point of contact? Yes.
Well, it should be well for us, Benfang, and he has asked Edouard. So that's what we agreed on. Okay. The second, this is one issue, and I think that we all agree on that. And the second issue, it's bad that Blaise is not here, but we can repeat or you can repeat it. The second part is what we talked about, the model and training the model in Mazira with Power Factory and scenario analysis, and then connecting to the neural network or any other machine learning, and particularly to get advantage of what has been done so far. To make the connection, those two, and then be back. I'll be back like a Terminator. I'll be back. I'll be back on February, and that's my plan. I will do my best to come back on February, and then we can make the update. The update. Here's Blaise. So just a summary, Blaise, just to make sure that we are all on the same page. So we said that we made an agreement anyway on the data part. What data, Peng said he will take care of that.
For Primo? Okay.
Anything that's great.
If you need anything, just ask Nouredine and he contact Edouard.
Maybe Edouard requests me to, you need a justification from your DKS project. I would like you to run an email.
You want me to contact Edouard?
No, it depends on how Edouard.
Okay, you let me. I can. We have two outlets.
Yeah, I can also do it.
Sure.
So that's one thing, because one of my important goals here is that we clear up the data issue.
So yeah, we need that. I mean, it's too long. It's long overdue. 6 months at least. And without the data,
that's why.
So this is a priority. Again, we were able to do a lot here because of the data, and so yeah.
And the data, I mean, Primo data most likely will be Sharat, will be the.
Yeah, exactly. So Sharat will be using it, but anyway, I mean, put it there, and then it will be available too.
So is the agreement already there? Is Sharat?
It seems, it's
his email. Benoit told me that there is an authorization for everything, all data not confidential.
And now it's starting his PhD.
Not confidential.
Sharat starts here and Sharat in France.
Oh,
With Benoit and I.
Okay, so this is my first objective.
Yeah.
And for me, we agreed. We are all on the same page.
Yeah.
Okay.
So it should be. I mean, let's say by end of the week. It should be done, okay? Else,
data.
Yeah,
Okay.
by the end of the month. So at least the email, put us in the sync and we'll see. Okay? That we see that there's a process and nothing is stopped.
Yeah, I thought you are. Okay, I thought you were asking me to finish the simulation.
Yes. The answer. Just the answer. Just the answer. So
What's the next step is to get the data?
okay, now I'm glad that we're on the same page on that. The second issue is now on the model, particularly on Mazira method. So Peng said that he will consider this the Power Factory with Mazira, okay, and define the scenarios. Those scenarios we discussed about the output, the output, and to keep it easy for the training, and then we use those scenarios for the training.
So yeah, that's
And the training, and then we close the loop with this training as use it for the control in case of we have this disturbance, and see how make the connection with what you demand.
So exactly, and that's we see the data and see how to
So this is the second step.
Okay.
And then I said that I'll be back like a Terminator. I'll be back. The plan is that I'll come back on February if I can. I will.
Okay, good.
I'll do my best.
I think like two weeks or something like that.
I try to say some weeks, okay? So I do my best.
Okay.
Because the problem is that if I want to stay 2 weeks, that means that I have to sacrifice my vacation week.
Yeah.
I did this time.
Yeah, already.
Sacrificed already the vacation time.
But so at least
And you know that for a professor, when you sacrifice
it's only week. Well,
again, you're fucked up. Okay? And I'm fucked up, and my family is really mad on me.
One thing important, it's Chinese New Year. Which month is it?
It's end of Jan.
End of Jan. So later in February, I would say.
8th of February. After 8th of February.
Should be okay, yeah. And if it's enough,
This is important because I don't want to come, well, if I come with the Chinese New Year, then I have to make party, not anything.
exactly. No point, no, so
No point, actually.
I
I have to make party
was,
rather than.
22nd January. So
okay, good. So yeah, 8th of Feb will be fully over.
Again, this is not guaranteed.
Yeah, no, I know, but they just
Two guaranteed.
yeah.
So-
Guaranteed.
Okay, just one comment on that. So I think in terms of scenarios, what I understood is there are two types of scenarios. One is just dealing with scenarios to see how the frequency regulation works. The part where, we have the
Response, it's the response to disturbance. Response to
disturbance. And then the second part is where you have these kind of
Losing of something.
losing a component. There are two different types of.
Oh, you mean, well, the first thing is that because before the disturbance, you need to make sure that you have your energy balance and power balance. Actually, it's even power balance, not energy balance. You have the power balance, and you make sure that over time the frequency is stable. This is base case. This is just the base case, and once you get that, then this is the first step. This is the first step.
Right.
This is the first step. Once you have that, which means that your physical point is stable at the beginning. Okay. Then you start scenario analysis, and those scenario analysis I suggest only having two scenario analysis for different operating points, because you need to have all those operating points. But for every operating point, you choose two scenarios. One is the step increasing in load, and the other one is losing generation or whatever. Okay, but we can imagine all the scenarios. This is relevant.
And then the objective is to.
And then to train. Objective is to train.
How the reserve battery is used to deal with this.
For example, if this is the target of the control, if this is the target of the control. Are you okay on that?
I'm trying to take notes.
The last question would be on the feedback, the closing the loop.
Yes.
How do you close the loop? So I have these scenarios, I get data on this. I do some classification on that in terms of. And then what would be the control action?
And then the control action is in operation. If such disturbance occurs, modality, of course, the conditions, which means that because you don't have exactly the same load that you have simulated, and in this case, you don't have exactly the same generation from the PV. So you have to assess the distance of that. And according to that distance, actually, you give a correct signal to the controller so that he can act to restore, for example, the frequency using the reserve. So that's you. In that case, the controller knows, because he has been trained, knows what to do quickly without calculating, without doing to make it fast.
So wait, so the scenario don't output only frequency incident or voltage incident, they also output the correct action.
Yes.
Gate?
That's not the this is the finality. I mean, this is the finality.
The power factory won't do that.
The power factory won't do that.
That will just give you the outcome of the scenario. You have to train
something. The scenario is the training.
So for the for the change of load, I just use step up or step up.
That's it.
Okay.
You can make it at the beginning. This is even for you. It's interesting. You can just make it as a classical simulation of power factory. I mean, it's for example, what you do is that during the time of the simulation, you program, for example, at 20 seconds. Example, at 20 seconds, you program the step in load. Load.
Yeah.
And that's without any training, just to see how it behaves, how your control is behaving. I mean, not the normal condition, but without any training, without anything, to see how your control is behaving. And you see what's the frequency response.
Yeah, frequency response.
And the voltage response, obviously.
So the control. So we want the training to map a situation with a correct action. That's the objective of the training.
The objective of the training,
is you map.
First is to see what happens.
Okay.
And secondly,
actually, it's close to what you've done. You know, you said that you told me that you have already made the training and you see what happened, and the distance, your distance is a multiplication factor for.
no, that's something else, but yeah, sure. Yeah.
It's close. It's that it's
Okay.
it's close.
Yeah. No, but so that's something else to be done, but okay. No, so yeah, at least see what happens, and then we can see.
Yeah, the gap we have now, it is, I think.
Yes, what to do? What to do?
Yeah, we don't know what to do.
Yeah. Okay, you don't know what to do. But at least what happened is already good. Yes, first step. But so, okay, you know, so Ibrahim will come next year as a, you know, Ibrahim. Anybody?
PhD.
Exactly. And so
He'll be.
I think this is exactly what I would propose him.
Yeah, he'll be good.
Was interested in the idea.
So I think basically this guy he can take the output scenario from bank simulation and try to make something out of it.
Yeah, so try to do something. Yeah, see, it's really a guy.
You're working on the Mazera model.
This is not even model zero, just Mazera, let's say, or model. Yeah.
Plus.
I'm not even sure.
Meaning that you are by yourself, autonomous standalone microgrid.
Yeah.
Okay.
Yeah, there's no green.
Because we have stuff there with.
No, you have to
not just.
We can come back to Mazera. It makes more sense on Mazera than Mac.
Oh, yeah, this is not just Mazera, what we did so far.
But we can put back what I've done on the level stuff. We can put it back in Mazera. It was our original plan. And
Right.
we thought we can use a grid. I mean, it's too different.
And simple, Benfeng, the simulation you have, do you have a grid connected Mazera or just a Mazera standard?
Islanding. Islanding microgrid.
So what we can do with that is, I mean, a Mazera with grid, and then you lose the connection to the grid. You are islanded, and what you do? That's a possibility.
Technically speaking, Mazera microgrid is islanding microgrid. If it is connected to utility grid, it will be that the converter over there is AC, DC, AC. So there's no statement about like your Mazera microgrid following utility grid. There's no such kind of thing.
Maybe the frequency of the control system will be slightly different.
So that's why we say
that's the way it is.
you need a frequency of Mazera islanding microgrid.
We can just look at Mazera. I think it makes more sense. Just Mazera with the frequency, or you will that and what to do that.
And I guess
different from what Subat has been doing, and so it's.
I guess
if you are by yourself, I mean, if you are in standalone, you don't have this idea of I come into a profile, I have to.
Yeah, so that,
So you lose this aspect.
But
and for me, you lose as well the cost.
No, because you still have cost, it's fuel, so you need to optimize the fuel, back to things, and still the two-stage stuff we had there, and so, okay. We're back to our original plan. We started with that, and we switched, we do the grid, it took us 2 months.
If you are back to this setup, where it is a stupid rule base, that if you are more solar than low to be charged, if you are less solar than.
You know what? Remy, don't talk to Suman because he's not coming back. Now we are going to submit a paper, and then he's done with this, I think. And then that's why I'm suggesting Ibrahim. For Ibrahim who is coming, then it's what we can do with.
But the PhD subject, I know PhD subject is more about training.
Robust. But then we will use that. But again, we won't look at the frequency and survive. Probably not.
Okay.
Because
delay.
Okay. Well, today was. The photos I had was only 5 minutes. The photos I had were only 5 minutes. So, just to make sure that, of course, don't hesitate actually to write me and ask me, and of course, maybe just let us know if you need maybe or explanation or whatever, so we can just advance all together.
Yeah, absolutely.
So don't hesitate. Now we have those two issues. Hopefully that we're all clear on that, at least on the objectives, even though we can still work on, I mean, count those two steps. And if it's okay, I think we have to stop here, unfortunately.
Yeah, sure, of course.
Thanks a lot. That was useful and at least useful.